So, so we started some recording. We were a little late in terms of time because I had some network issues. So let's jump into the solution for the paper. If you guys have any problem that you tried and couldn't solve, please give me those numbers. I'll try to help you for those. And if not, then we can just look at it over here. Question number B, another thermal problem. Let's have a look. 25B. A mass of 24 gram ice at minus 15 degrees Celsius is taken from a freezer and placed in a beaker containing 200 gram of water at 20 degrees Celsius. Data for ice and water are given in 3.1. So we have this whole thing. And then the question says, calculate the quantity of thermal energy required to convert the ice at minus 15 degrees Celsius to water at 15 degrees Celsius. So have a very good look at the temperature and also at the words for the state. Calculate the quantity of thermal energy required to convert the ice at minus 15 degrees Celsius to water at 0 degrees Celsius, which means we are trying to convert. First, we are going to increase the temperature of ice state from minus 15 to 0. Then we have to convert 0 degrees Celsius ice into 0 degrees Celsius water. So this is a two-step process. So we're going to need information from here. As you can see that here the units are all joule per kg. So we don't have to go for the botheration of unit conversion very carefully, but just take the numbers over here from directly. So if I write the amount of heat over here, this is going to be mc delta theta plus mlf, which is going to be given by 24 gram of ice, which is 0.024 into 2.1 into 10 to the power 3 into 15. This is the temperature heat required to raise the temperature to 0 degrees Celsius plus 0.024 into 3.3 into 10 to the power 5. So that's going to be the energy required for this process. And then the question says, assuming that the beaker has negligible mass, calculate the final temperature of the water in the beaker. So that's pretty simple. Heat absorbed should be equals to heat given up. But in this case, the heat that would be absorbed by the hot water would be used to increase and reduce the temperature at the same time. So let me just try to draw a figure for this one in the preferred way that I usually show. The beaker water temperature was initially at 28 degrees Celsius. So this is our hot object, and our initial cold object was minus 15 degrees Celsius ice. So first of all, this has to be moved to increased temperature of 0 degrees Celsius ice. Then ice should melt into 0 degrees Celsius water. And this one should have its temperature rise as the temperature of the hot water, the beaker water, drops eventually to a final unknown temperature. Let's say theta degrees Celsius, which we don't know. We want to calculate this out. So this is our unknown. How much is this? So heat is absorbed over here, which we calculated right over here, and it will be given up by this water, hot water, to drop its temperature from 20 degrees Celsius up to this point. So we actually calculated this much amount of it. Have a very good look. We actually just calculated in option number 1 this much amount of required energy. We did not have involved how much heat energy to be absorbed by the ice melted water to raise this temperature from 0 degrees Celsius to theta degrees Celsius, which is our unknown. So we need to include this within our equation so that we can equate it on the both sides. So I'm just going to write it over here. It answer koto ashe? Can someone help me with the number? I could pick it up from the mark scheme as well. Is my voice heard properly? I mean, kotha thik mon shona jacche?
Yes, sir.
I'm just asking because I've had this network issue since yesterday evening. It couldn't be solved. Then সকালে উঠে একটু ঝাই পড়তে দিছি. But then they gave me some actual instruction for how to approach my computer. Apparently the problem was with my computer, not with the network settings. So I did some network reset and learned new stuff. I pulled up the wrong mark scheme. Okay, that's that. 25. So thermal energy heat required to convert আচ্ছা এখানে আমরা this amount of energy that we found over here is to 8700 joule, and we're going to use that to calculate the final temperature. So this was 2700 joule. So for the remaining of the problem, we can go by this 2700 plus mc delta theta. This for the ice water equals to mc delta theta. This for the hot water of the beaker. These two m's are not equal, but I'm just writing these equations out to make sense with you that what we're trying to do over here. Which is going to give us 2700 plus 0.024 into water has a specific heat capacity of 4.2 × 10⁻³ So 4.2 into 10⁻³ into theta minus 0. This is the mc delta theta for this one, which should be equals to the beaker water 200 gram, that is 0.200. You can also choose to write only 0.2. I'm just writing 0.200 to keep me in understanding that this is the 200 gram water into 4.2 into 10⁻³ into 28 minus theta. So that's your equation. Solve it carefully for the value of theta. Solve for the theta value কত আসে? Help yourself. কত আসে? This is a number that I'm getting, which apparently is not correct. So What was my mistake? Oh, I'm supposed to use 8676. What is happening? Two hundred to 4.2. আমি ক্যালকুলেশন কোথায় ভুল করছি? This was not 2700. This was 8700. No wonder. To be more precise, this energy was from the earlier question was 867. This is the value that they use for the further calculation. সকালে কি তুমি বিড়াল পাইছিলা ওই জন্য ফোন দিছিলা? একটু আগে ঠিক হয়েছে কিছুক্ষণ আগে। So I'm sorry for the wrong value. This is supposed to be 8676. 8676. So I'm gonna write 8676 over here. বাকিগুলা ঠিক আছে, I believe. 8676. This is wrong. 23520 minus 8676 equals to divided by 940.8. 15.77. Oh, 16 degrees Celsius. Yeah, got it. So this is supposed to be a final answer. You can write in 2SF or 3SF, however you feel like. If you 2SF would be 16 degrees Celsius. That's it. You just write 16, or you can write 15.8. That is also equally acceptable. আচ্ছা, এই ম্যাথটা অ্যাকচুয়ালি খুব একটা ডিফিকাল্ট না, বাট দেয়ার ইজ এ রিজন আই পিকড আপ দিস ম্যাথ। ক্যালকুলেশনটা কি বুঝে গেছে সবার? আমি একটু ভুল করছিলাম, এই নাম্বারটা পিক আপ করতে ভুল করছিলাম। হ্যালো লবান, ক্যালকুলেশনটা কি বুঝছো? Heat was absorbed by the cold object to reach up to the same thermal equilibrium temperature as heat was lost by the warm object to reach to the same temperature as the thermal equilibrium. So together we have this whole thing. The reason I picked up this problem because this whole process actually worked because of one underlying principle. Let me explain what that is. The warm water, whenever we had 220 degrees Celsius of water, which was 200 gram, we had minus 50 degrees Celsius ice, which was only 24 gram. What you need to understand, the amount of heat energy that this hot water or warm water could give out was enough for the total amount of ice to raise its temperature to 0 and then melt all the way and eventually have the temperature go up all the way over here. So that's one way. Sometimes it can also happen that it is possible that in some cases the total final state of the object is not gonna be only water. I mean, if you have too much of ice over here, for example, if I just write over here, let's say maybe 240 gram of ice, let's say. So if we have about 10 times more ice over here, I can show you by calculation that in the final mixture, we're gonna have some ice and some water with each other at 0 degrees Celsius. And for those kind of scenarios, it is still in thermal equilibrium, but the melting of the ice would not be complete. This can actually happen, and these kind of problems can show up. I'm not sure if we have one of those in the worksheet, but I'm just gonna show you the calculation for this problem, considering that we are starting not with 24 gram ice. Let's say we are starting with 240 gram of ice. So with the similar problem, let's say we're going to merge 240 gram of ice at -20 degrees Celsius with a 208 degrees Celsius of water with 200 gram within the beaker. The beaker has negligible mass, no energy loss or received from the surrounding. So how about we approach this problem? Have a look. The coolest the warm water can become. I'm trying to show you multiple steps over here first, and then the logic is going to become much too clearer for you. Heat energy given maximum heat energy that this water can give without freezing itself, I mean as it brings itself to 20 degrees Celsius, is gonna be 0.200 into 4.2 into 10 to the power 3 into 28 minus 0. So if I can calculate that number, this is 23520 joule. This is the maximum amount of heat energy that the hot water can give out before reaching to 0 degrees Celsius. Now let's try to find out another value of energy, that if we want to make all of this initial substance -15 degrees Celsius ice at 240 degrees Celsius to convert into 0 degrees Celsius water, how much energy is going to be needed? Let's say I'm going to write this as Q required. This is going to be MC delta theta plus MLF. So 0.0, in this case I wrote 240 grams, so this is going to be 0.240. 0.240 into 2.1 into 10 to the power 3. Delta theta would be 15 minus 0. This is the MC delta theta for the cooler ice, then at -15 degrees Celsius, plus 0.240 into the latent heat of fusion of ice, which was given over here to be 3.3 into 10 to the power 5. 3.3 into 10 to the power 5, which gives us how much? This is 7560. So I just got two numbers. Try to have a look at these two numbers and try to get an idea. What do they possibly mean? What I'm trying to show you, if we want to bring down the temperature of the 20 degrees Celsius all the way down to 0 degrees Celsius, the maximum amount of heat that it can give out is this much. And if we want to melt, if we, all the -15 degrees Celsius ice into 0 degrees Celsius as well, the required heat amount would be this much. So we have to input this amount of heat. You can see these two numbers are definitely not equal. The heat energy that could be required to melt all the ice is far more bigger compared to the amount of heat energy that could be supplied from the warm water. This essentially goes on to prove that that ice that we started at the beginning is not going to melt completely. So here's what's going to happen. I mean, the amount of required energy to increase the ice temperature up to 0 degrees Celsius, which is the MC delta theta, this is 7560. This is definitely going to happen because we can get 7560 joule of energy out of this amount. So temperature of the hot water is going to drop from 20 degrees Celsius, and temperature of the -15 degrees Celsius ice is also going to rise So that's gonna happen. So this is gonna reach to 0 degrees Celsius ice without any trouble because it can receive that amount of heat energy from the hot water, warm water, and the temperature is gonna drop somehow. And then the ice is gonna start to melt. And the temperature of this is gonna slowly start to drop. And there would come a certain point when all of this hot water would eventually reach 0 degrees Celsius, but all the ice wouldn't be melt because you just don't have enough energy to melt all the ice, because the ice, total amount of ice for the whole melting process is going to require this much energy. There's a reason I wrote these two numbers differently to utilize these numbers for the calculation. So ice would not be completely melt, which means your final composition of the whole mixture is going to be, you're going to have some liquid water, you're going to have some unmelted ice, both of which are maintained at 0 degrees Celsius, which is a thermal equilibrium scenario. That's how this whole thing is going to work out. This can happen. এই আইডিয়াটুকু বুঝা গেছে কিনা? এখন কতটুকু আইস থাকবে, কতটুকু ওয়াটার থাকবে সেটা আমি ক্যালকুলেশন করে দেখাবো. I'm going to show you that calculation. But do you understand the concept that we have over here?
Yes, sir.
So let's try and find out that how much ice would be melted. This is pretty simple to do. Let me show you. For the increase of the temperature of 0 degrees Celsius water to for the increase of the temperature for the ice into 0 degrees Celsius, this much amount of energy would be absorbed. So if I subtract this amount from this amount, so if I just do this, 23520 minus 7560, which gives me how much? 23520 minus 7560 is 15960 joule. After heating up the ice to 0 degrees Celsius, this much heat energy would be left within the warm water for the further melting process. So this is the amount of heat that can be used for the melting process of ice, which is now at 0 degrees Celsius. So then the remaining formula is very simple. Q equals to MLF. So M would be given by Q divided by LF, which is 15960 divided by 3.3 into 10 to the power 5. This gives me 0.04836 kilogram. So the amount of heat that I would have left within the warm water after heating up the ice can be used to melt this much ice into water, which means out of this total 240 gram of ice that I initially began with, this much ice will be melted. The remaining would still remain as ice. And because this much ice would be melted, this ice melt water would join with that 200 gram of water. So if we do further calculation, we just add up these numbers, therefore remaining ice equals to 240 minus, should I go in gram? I can go in gram. If I multiply this by 100, I'm going to get 48.36.
$191.64.
Yes, we get 191.64 gram of ice and combined water. I mean, using the word combined because this water is going to get added to the 200 gram. This is simply going to be 248.36 gram. So the end temperature of the mixture would be 0 degrees Celsius. This is the final state of the whole mixture for a problem if we had 240 gram ice to begin with. So this is also a type of a scenario that can happen, that you might not have enough energy in your warm body to melt all of your ice and eventually lift its temperature to the final value that we want it to be. So it's a possibility, and if this kind of math does show up, it requires a bit more calculation. You will be definitely rewarded with marks for this kind of calculation. For example, how did I know that we have to go for this mechanism and not for the earlier mechanism? Because I calculated the two amount of energies required first, and that going on to show me that I cannot, or we cannot have a mixture only made up of water for this problem. So you're going to have marks for doing this calculation and eventually picking up the decision that yes, the final temperature of the mixture is going to be 0 degrees Celsius, and there'll be some ice still unmelt, because so that decision making process is going to have some mark within itself. And then the remaining part of the calculation, that how much ice would be actually melt, is done by the subtraction and division. And then we came up with the final answer by addition, by subtracting the ice amount and adding the water amount with the earlier amount, and also confidently mentioning that the final temperature is going to be 0 degrees Celsius. So all of these steps are going to have individual marks attributed towards them, but it's important that you understand that this can happen. Any questions so far? Palaban? Okay. So this was number 25. At one particular time, the resistance thermometer is 2040 plus or minus 20 degree. 2040, something over here. 2100 40 is 2 divisions above this thing. So 1 division, 2 division is right here. This point, we get 15 degrees Celsius. I'm 26 at apart because they have given a bit of an uncertainty over here, and they're asking determine the temperature in Kelvin to an appropriate number of decimal places. So should we have to take into account this plus or minus 20 degree or not, 20 ohm or not? I forgot about that. 26. 2040 plus minus 20 degrees, 20 ohm corresponds to 15.0 plus minus 0.2 degrees Celsius. So TK, Kelvin temperature is gonna be, so here when okay, yeah, interesting question. So I'll go for number B a little bit. It's a very simple question, but because there's a bit of an uncertainty showing up over here, I'm gonna help you a little bit for refreshing your memories for how to do uncertainties in your S. We have a graph for the resistance thermometer. We have the resistance versus temperature in degrees Celsius given over here. At one particular temperature, the resistance of the thermistor is 2040 plus or minus 20 ohm. Determine this temperature in Kelvin to an appropriate number of decimal places. Okay. So if we take a good look at the graph, we're gonna find out that every division over here, every vertical division represents 20 ohm resistance. So 2040 is gonna be 2 divisions above the 2000 line, which if we plot on the x-axis, we're gonna get exactly 15 degrees Celsius. So right over here. Now, finding out the temperature out of the graph is pretty simple, but we need to convert that into Kelvin temperature, and also we need to take into account for how much this would mean. So this is the important bit over here. The information that I want you to see, that how do we convert 20 ohm amount of vertical axis problem with the horizontal axis, is actually pretty simple. Just try to have a look on the graph to understand for equal number of divisions that you have on the scale. What I'm trying to mean is, if you see over here, just look at on this 10 by 10 box. For a rise of 200 ohm in resistance, you have a change of total 2 degrees of temperature. So if you consider this scale, for every 200 ohm, the variation is 2 degrees Celsius. So for every 1 ohm, you're gonna get something. For every 20 ohm, you're gonna get 0.2 degrees Celsius. Does it make sense? This is just basically converting the scale for the sake of uncertainty. If this was 15, I'm gonna go for 15. If this was 5, I'm gonna write 5 over here and find out that appropriate ratio. So this is just basically depending upon the graph scale conversion, that how much ohm is relevant for how many degrees Celsius. এই কনভার্সনটা কি বুঝছো বলবান গ্রাফ থেকে যেটা নিলাম?
জি স্যার।
আর কোশ্চেন? আচ্ছা, বুঝতে বললেন, good. So we get this information and then we can simply go for the by reading by the graphs. We can write 15 degrees Celsius plus or minus 0.2 degrees Celsius, which needs to be converted into Kelvin. So showing this number actually scores you 1 mark, and then the Kelvin temperature would be 15 degrees Celsius, sorry, not degrees Celsius, T15 plus 273.15. Here they actually considered the 0.15 to be within part, allowed 273.2. They also accepted 1 decimal place as well. What is important for you to understand that the reason they are going for this much precision, because on the x-axis, if you have a look over here on the x-axis, each smallest division represents 0.2 degrees Celsius. So considering this fraction 0.2 degrees Celsius, it's important that we take into account this remaining part of the decimal place fraction within our conversion formula. It's important. বুঝতে পারছি?
না স্যার।
মানে হচ্ছে because the smallest division on the x-axis is 0.2 degrees Celsius, which means this is a 1 decimal place. So আমরা যখন 15 degrees Celsius কে read off করতেছি, this is actually not only 15 degrees Celsius. We should read this temperature as 15.0 degrees Celsius. So we already have the inclusiveness of 1 decimal place within our value, because the step size on the x-axis is 0.2. So we can have 12.2, 12.4, 12.6, 12.8, 13, 13.2, 13.4, 13.6, 13.8, 14. It goes on like that, which means we have the inclusiveness of 1 decimal place automatically within the graph. So because we have that, whenever we are doing the addition of 273 with the degree Celsius temperature to convert it into the Kelvin temperature, it's important that we take at least up to the first decimal place of that conversion number, because the actual number that we have to add to make some degree Celsius temperature into Kelvin temperature is 273.15. This is the actual conversion value which I showed you at the beginning of the lecture of this chapter. But because this graph only cares about the first decimal place, if you want to write this as 273.2, this is also equally acceptable. And the final answer they expected to be 288.2 Kelvin. It's important that you write this whole answer, although it looks like a 4SF answer, but you need to write this answer up to the first decimal place, because the graph is covered up to the first decimal place. বুঝতে পারছি?
Yes sir.
সবাই বুঝছো? পোলাওয়ান? Everyone else?
Yes sir.
Okay. 27. The kinetic theory of gas based on simple check the Habibi question. এরপর হচ্ছে PV equals to 1/3 mc square একটা প্রুফ, এটা তোমরা করবা। আচ্ছা, আমি এই কোশ্চেনটা একটু দেখাই। The molecules of an ideal gas have a root mean square RMS speed of 520 meters per second at a temperature of 27 degrees Celsius. Calculate the RMS speed of the molecules at a temperature of 100 degrees Celsius. This question is not difficult, but it can prove to be significantly, what can I say, tricky, because there are I think there are 2 common traps that students fall into. First of all, half mc squared equals to 3/2 kT, which brings us c squared is proportional to Kelvin temperature. So the 2 locations where the students make mistake is that sometimes, not always, sometimes do not convert the degree Celsius into Kelvin. Answer will mismatch. Not gonna work. And also sometimes they don't forget to do the square. Have a look. This is root means square, but this is a square over here. So it's important that you include the square. So the final equation that should look like, I can write it in this manner. Let's say C1 square divided by C2 square should be equals to T1 by T2, which can translate into 520 squared divided by C2 squared equals to this is 27, so I'm going to write 300.15. You might wonder, why do I bother to bring about 0.15? Because of the accuracy of calculation, nothing else. And divided by 100 degrees Celsius is going to be simply 373.15. Solve this calculation for the value of C2 only. So you do this ratio, do the calculation, and finally don't forget to do the root over. Get the number in 3SF, because I would assume this number is also in 3SF.
$480. 580.
ছোট হইছে?
No, sir.
কত আসছে?
580.
আচ্ছা 580.
No, sir. 3SF.
Okay. Everyone else, do your calculation. If it's good, okay, keep quiet. If it's not,
Yes, sir. 59.8.
so yeah, that's the idea. So এই ভুলটা যাতে না হয়, এক নাম্বার হচ্ছে এই ডিগ্রি সেলসিয়াস টু কেলভিন কনভার্সন যাতে ভুল না হয়, আর হচ্ছে স্কয়ারটা যাতে ভুল না হয়। সো এইটার জন্য এই ম্যাথটা দেখানো। এছাড়া ইটস ভেরি সিম্পল, জাস্ট a basic proportionality formula. If you know your shit, you should be able to do that pretty easily, no big deal. আচ্ছা, এরপর আমাদের আছে হচ্ছে 28 কেউ করছে এই পর্যন্ত? না করলে 28টা ট্রাই করো। I would like all of you to try this problem. This is a problem where we mathematically find out the amount of heat loss to the surrounding. I'll be right back. পারা গেছে এই প্রবলেমটা?
Yes, sir. Correct.
The idea is very simple. The idea is that এখানে কোশ্চেন একটা জিনিস বলে দিচ্ছে যে 2 মিনিটে আমাদের the amount of total amount of water evaporated from the container is 106 gram in 2 minutes. So you have to understand that all the heat that is supplied from the heater that was actually fed into the water within these 2 minutes was not actually used for the boiling, because the temperature is hot, so you are losing heat to the surrounding. So you have to calculate that how much heat was lost to the surrounding within this process. It can be done pretty easily. You can calculate exactly how much heat is needed to boil this much water. You find it out by the combination of these two information, MLV, and then you calculate how much heat was actually supplied to the system by the product of these two things. So you get the heat supplied by 2.40 into 10 to the power 3 into 120. That's your heat supplied. And the heat that you actually used to boil the water is going to be 106 into 2260. The difference of these two is actually the heat lost. So you calculate that, and then because the question is asking us to give the answer in rate of loss, which is power, so the final thing, power lost, would be simply that subtraction value Q lost divided by 120. Be careful to do the minute to second conversion in every single case you are using the time, and that's pretty much it. আচ্ছা, এর পরের প্রবলেমগুলো খুব বেশি ডিফিকাল্ট না। should I help you with this one? 30 না 30 তোমরা নিজেরা ট্রাই করবা। It's a bit difficult, but I want you to try this. If you can solve this, I'll help you. No video. আমি টেম্পারেচার একটা স্পেসিফিক প্রবলেম দেখাতে চাইছিলাম, সেটা হচ্ছে স্পেসিফিক ক্যাপাসিটির গ্রাফে একটা প্রবলেম ছিল, এটা যে কোথায় আছে। No, I'm gonna do 31 first. So I'm gonna do 31 for you, and then I'm gonna go for this one, 36. 36 is a pretty interesting problem, like a really interesting problem. So I'm gonna go for 36. So 31 একটু দেখাই আগে। 31 will say the volume of an ideal gas in a cylinder is this much meter cube at a pressure of this much Pascal and a temperature of 297 Kelvin as illustrated in figure 2.1. So we have this whole scenario. The thermal energy required to raise the temperature by 1 Kelvin of 1 mole of gas at constant volume is 2.5 joule. This is an important information for you to understand what this means. Thermal energy required to temperature by 1 Kelvin of 1 mole gas, 1 mole of the gas at constant volume is 12.5 joule, which is basically sort of like an information like molar gas constant. So I can say that this quantity, which I can write, let's say by a random variable, thermal energy, let's say I'm going to call it X, that is going to be 12.5 joule per mole per Kelvin. That's the value of this whole thing. The question says the gas is heated at constant volume such that the internal energy of the gas increases by 95 joules. Calculate the amount of gas in mole in the cylinder. So that's pretty simple. You go for PV equals to nRT and calculate the n out of this equation. You have the pressure given, you have the volume given, you know the molar gas constant, the temperature is also given in Kelvin, so no need requirement for conversion. Place all the numbers P, V, R, T, calculate the value of n, and you're good. Number 2 says the rising temperature of the gas. Now, we have this value, 95 joule, we have the mole. So you can directly go for a formula like this. For example, I could write that 95 Zara, are you calling me?
No, sir.
Never mind. So we can directly go for this in this formula that 95 should be equals to the mole number of the gas multiplied by the X multiplied by the delta T. This is basically MC delta T delta T formation, but in this case the mass was converted into mole because this was joule per mole per Kelvin. So sort of like E equals to nRT. That's an expression. So that's one way to do this problem. Or if you are not comfortable remembering this, if you don't want to remember this, this is a very simple way. You can go by unitary method as well. So if you want to go by unitary method, this is how we do it. 95 joule energy, not 95, I'll start by 12.5. That is 12.5 joule energy increases the temperature of 1 mole of gas by 1 Kelvin. Therefore, 1 joule increases it by 1 by 12.5. Therefore, 95.0 joule increases it by, for this many mole, whatever you get from this amount, you place it right over here. So you write 1 into that number into 95.0 divided by 12.5. This would also get you this number, but I'm not sure whether the examiners would actually like to see an application of unitary method at your level. So I'm just going to check the mark scheme for this one. 31. Q delta Q goes to MC delta T. So in this case, the M was actually the mole number, like I showed you earlier. So you can find out the delta T equals to 40 Kelvin, which was, or allow 2 marks for correct answer with clear logic shown. So if you don't go for this formulation, if you just go by unitary method, they're gonna also equally accept that. If you have a look at the examination report, rather surprisingly, few candidates use the execution delta Q goes to NC delta theta. The majority of correct answers were based on a two-step approach, calculating the energy for 0.19 mole to increase in temperature by 1 Kelvin, then using the given energy input. Okay, no worries. Works for me. In number 2, it says, use the answer in part 2 to show that the final pressure of the gas in the cylinder is 2.95 into 10⁵ Pascal. Now, this is a part that we need to do carefully. We have a bit of a rise in temperature, delta T, and we had a bit of initial temperature, and we are asked to show that the final pressure of the gas should be this much. Now, here's the deal. If you should recall, any type amount of idle gas is about by this ratio, PV by T equals to constant. For this scenario, the question says that we have kept the volume constant, which basically means that P by T, this ratio should be a constant. So if I go ahead to make this into a formula, so P1 by P2 should be equals to T1 by T2. Here, the initial temperature was 297 Kelvin, and the question said that we increase the internal energy. So obviously there will be temperature increase. We just calculate the delta T over here, which from the mark scheme I can quote, it is 40 Kelvin. So the new temperature is going to be 297 plus 40. So you place the value of initial pressure right over here, which is 2.6 into 10 to the power 5. Then you are trying to find out the new pressure P2. The initial temperature was 297 and the final temperature is 297 plus 40. And that basically solves your problem. The idea is to recall that ideal gas equation follows this formula, and from there we can go forward. It's not difficult, pretty simple. So if you have a question, please ask. Number B says the gas is now allowed to expand. No thermal energy enters or leaves the gas. The gas is now allowed to expand. No thermal energy enters or leaves the gas. The gas does 120 joule of work when expanding against the external pressure. So this is the minus W. Work is going out of the system. The system does 120 joule of work for the gas while it's doing some work against the external pressure, which is atmospheric pressure, obviously. State and explain whether the final temperature of the gas is above or below 297 Kelvin. Now, this is the part that is pretty easy to explain. If you recall, first law of thermodynamics, let me have a look. Delta U was given by Q plus W. Recall, delta U is the amount of increase of internal energy, Q is the heat supplied into the system, W is work done on the system. In this case, work was done by the system, so W is going to be negative. The question says no thermal energy enters or leaves the gas, which means Q is going to be 0. This essentially means delta U should be also negative, which means the total amount of internal energy of the system is actually reduced. That would essentially mean for an ideal gas system, the temperature should also be below 297 Kelvin, because the energy of a ideal gas system is only the kinetic energy of the system, which only is coming or related to the temperature of the gas. So if I was writing this answer, I'm just going to write the equation. The first of thermodynamics states delta U equals to Q plus W. No energy was supplied to the system, so Q equals to 0. Work was done by the system, so W is negative, which essentially dictates change of internal energy, delta U is negative, because ideal gas internal energy is directly related to its temperature. So temperature decreases. That's it. That's how I would write the answer. But just for the case, let's have a look at the mark scheme, what they have. Change in internal energy is this much. Internal energy decreases, delta U is negative, kinetic energy equals decrease. Change in internal energy is what? What is this? Change in internal energy. Did they ask us to calculate? The gas is now allowed to expand. No thermal energy. The gas does this much. Change whether the final temperature of the gas is above or below 397 Kelvin. Oh. Where does 25 come from? Oh, acha, বুঝতে পারছি, this is not division, they meant it to be or. আরে বলুন মার্কস স্কিম এখানে আরেকটা স্ল্যাশ মার্ক দাও, make this slash double slash so that you don't mess it up as a division line. Changing internal energy is 120 joule, or some kids can consider it to be 25 joule as well, but the total change of energy is actually decreased. The reason they're accepting both of these numbers is for one reason, is that the question says the gas is now allowed to expand, no thermal energy enters or leaves the gas, and the gas does 120 joule of work when expanding against the external pressure. So for this question, 120 joule of energy was leaving from the system, and earlier in this question we said that 95 joule of energy was fed into the system. So the altogether, so another way to judge this problem is that you can also consider, as per the question, that delta W can be minus 120, and Q, because the question says that this part, so you can consider this part should be 0. That's my best way, that's my, in my opinion, the best way to go. But the examiners also accepted if some student consider the earlier scenario of 95 joule of heat energy addition, and you place this as plus 95 over here, and consider the delta U, which is still going to be negative some value. So if you still bring about this 95 from the earlier question, you're still scoring the mark, which I would recommend not to do, because the question over here dictates that no thermal energy enters or leaves the gas, which is the new scenario. So, but still, if you consider 120 joule of energy loss, that is acceptable. Or if you do that subtraction of these two numbers, you're going to get 25 joule of energy loss. That is also equally acceptable. That's why we have two accepted numbers over here. I would recommend not to go for the 25, but the examiners seem to be, what can I say, hearty to accept either of these answers. Thank you. So changing internal energy is 120 joule divided by 25 joule. Internal energy decreases, or delta U is negative, kinetic energy of the molecules decreases, so temperature is lower. If you have a look at the examiner's report for this one, B says there was considerable confusion of ideas when answering this part. Some suggested that the temperature would rise because the gas had done work, which is wrong. In many answers, a link was attempted between delta U, Q, and W, but frequently the signs of what these changes were not clear, leading to the conclusion that the internal energy would increase. Okay, so if you're using the first law of thermodynamics, it's important that you clearly state what's gonna be the sign of each of these variables for your used equation. Beats me. I hope this question is clear. Any question, Poloman? None, I guess. If you have question, please ask me, or you can look back into the lecture if you feel like, and ask me questions in the later class as well. I'll be glad to answer your questions. All questions are equally appreciated. Some questions are more appreciated than other, but all questions are appreciated nonetheless. এগুলো খুব একটা difficult না, but if you can only figure out whether it's difficult for you or not if you try. So I highly recommend that you try. I'm going to talk to you about the concept for number 36. Let's have a look. Question number 36 says, a student states quite wrongly the temperature measures the amount of thermal energy or heat amount in a body. Statement explain two observations that show why this statement is incorrect. Four-mark question. Without looking at the mark scheme, can you think of an answer that might score you all 4 marks? A student states quite wrongly the temperature measures the amount of thermal energy or heat in a body. State and explain two observations that show this statement is incorrect. What could be these two observations? Now, if I was doing this answer, I would say temperature actually dictates the direction of heat energy flow. Heat energy always flows from high temperature to low temperature. And the other thing that I'd say that it is possible for an object that is small to have a high temperature, really high temperature, but a very small amount of energy. Whereas a large object can have a huge amount of thermal energy within itself, but a pretty low temperature is possible. One of the interesting interesting example that comes to my mind is that uh, to differentiate between the idea of thermal capacity and temperature, there is a certain example. I think I'm not sure, I can recall exactly whether it was from an O levels question or it's from an A2 question, but I'm going to tell you the scenario anyway. Is that there was a question which went like that. Welder is doing some welding and sparks of hot metal, glowing hot metal, is falling on his hand skin, but he feels nothing. Why is that? Now you need to understand that whenever a welding happens, the temperature of the metal goes so high that they actually melt and joins together. So at that location, the temperature is very high. So all the sparks which are coming out, they are coming out of a source which has the temperature as hot as melting that metal. But as those sparks fall onto are falling onto the welder's hand, he's not feeling anything. I mean, one pretty weird choice of answer can be that his senses are numb, or let's say his nervous system is not working. But that's not physically explaining for the requirement of this question. The correct response to this question is somewhat like this. The individual sparks are coming off at a really high temperature, but because they are so small, or their mass is so small, the total amount of heat energy contained within them is extremely small. So try to understand, if you have a very small object heated to a very high temperature, you can do this by a very small amount of heat. But if you have a large object, you're going to need a large amount of heat. So even if those sparks are heated to a really high temperature, because each of these sparks are extremely small, they do not bring about any significant amount of heat to be felt by the skin. So they can simply fall on the skin can absorb that heat and perfectly be okay with it, even though the temperature is quite high. But it's not the temperature that we sense. We actually sense the type of heat energy flow through our body. Let me put it this way. Our sensation of physical temperature through our nervous system, through the skin, actually tells us, are we losing heat or are we gaining heat? That's basically it. For example, if you go on an icy environment without much to protective clothes, you're going to start losing heat from your skin really fast. Your body is going to sense that as a sensation of cold. Vice versa. If you go out on a desert, on a midday sun, pretty likely the temperature of the desert at a midday sun is much higher than 37 degrees Celsius, the typical body temperature of a human being. So you're going to feel like that your body will start to receive heat. You're going to feel warm, significantly warm. So, and the way we can actually differentiate between different temperature objects is also by the rate of heat exchange. One of the very common example is that passerby sits on an iron bench on a park. The iron bench feels cold. What does it mean? There is no way to guess that the temperature of the atmosphere, temperature of the soil, temperature of the trees, and temperature of the iron bench is anything different. They are all part of the environment, which means all of their temperature is exactly the same. But iron, being a good conductor of heat, can take away heat from our skin pretty rapidly. So the rate of heat loss is much higher for the parts of our body that touch the metal surface. For a small duration, that is, not for a very long duration. But for that duration, those parts of our body which are in contact with the iron bar feels the iron bar to be much cooler, because we do not essentially sense the temperature by its exact numerical value of temperature. We sense, our body senses the temperature of an object by what rate are we losing or gaining heat. If you're losing it pretty rapidly, we consider it to be really cold. If you're gaining, if you're losing it slowly, we consider it to be a little less cold. If you don't lose temperature to any object, we feel it to be at the same temperature. So that's the difference. I actually moved quite a bit segue from the actual question. The question was here was a certain true observation that show why this statement is incorrect. So if I was writing this for two observation, the first observation I'm gonna write that flow of heat energy always depends on the temperature, not on the amount of heat. I mean, or I could write that small objects containing a less amount of heat but at a higher temperature is going to lose heat to a large object containing a higher amount of heat energy but maintained at a lower temperature. That's one thing. And the other point that I would make is objects which are at the same temperature but have different masses can have different amount of temporary thermal energy within them. So bigger objects will have bigger amount of thermal energy. Smaller object is going to have smaller amount of thermal energy within them, even if they are all kept at the same temperature. So temperature is not a measure for thermal energy. It's actually a measure for what would be the direction of the energy flow if we keep them in thermal contact. So if I have a look at the mark scheme for this question, because I'm very interested to see how the examiners appreciated this, the answer of this question, I'd like to see that. This was question number 36. Two objects at different mass at same temperature is possible. Example, two same material would have different amount of heat. Temperatures show direction of heat transfer from high to low regardless of objects. When substance melts or boils, heat input but no temperature. Yeah, this is also another example that I didn't think about. Yes. For example, for the case of state changes, we have to put in heat, or we can give out take out heat for the case of solidification or for the case of condensation. But for all of those cases of state changes, temperature remains constant. So temperature doesn't actually determine the amount of heat energy. It doesn't. Makes sense. Most answers included only one observation, namely either melting or boiling, which I didn't think about at all. Weird. Very few discussed temperature difference as indicating the direction of thermal energy transfer or made a reference to either mass or to specific heat capacity. Many answers were a mere statement that temperature measures the degree of hotness of a body. Degree of hotness reminds me of the hot crazy matrix. Anyway, just out of curiosity, do any of you know what is a hot crazy matrix? Did I ever talk to you about this? Anyone?
No, sir.
hot chocolate effector moto.
Huh?
Hot chocolate effector moto jeta.
It's a graph. Okay, if you do not know this, I highly recommend that you find this out on YouTube. Hot crazy matrix. Good research, to be honest. There's a reverse version of that as well, which is also quite enjoyable, but not as much. Okay, anyway, we'll move back to the thermal capacity. The question that I was trying to get to, or I was very much willing to get to, number B. Have a look. Try to pay close attention to this question because this is a new type of measurement that we're going to look into this question. So if you have questions, please ask me immediately or raise your hand. A thermometer and an elliptical heater are inserted into holes in an aluminum block of mass 960 grams as shown in figure 3.1. Aluminum block, and there is no lagging around. There is no insulations around. The power rating of the heater is 54 watt. The heater is switched on and readings of the temperature of the block are taken at regular time intervals. When the block reaches a constant temperature, the heater is switched off and then further temperature readings are taken. The variation with time t of the temperature theta of the block is shown in figure 3.2. So this is what is happening. We have a temperature versus time graph. The scale is not given, but the question says that we are recording the temperature at regular time intervals, maybe per second, maybe per minute, I don't know. We're starting from room temperature, that's why it's not having a 0 point. We're starting from room temperature. As we start on the heater, the temperature of the block, which is read by the thermometer, slowly goes up. And as the object becomes warmer and warmer, it starts to lose heat to the atmosphere more rapidly. There is a certain point when this graph becomes horizontal, which you can see over here. What does this mean? You have to understand, the heater was switched off when this graph was corner, has a sharp corner over here. But before that, as the temperature of the aluminum block slowly goes higher and higher and higher, at one point, the temperature is not rising anymore, even though the heater is kept switched on. The reason is that at this temperature, the aluminum block and the all setup, all of the setup is so hot that its rate of heat received is equal to rate of heat loss. So you do not have any more heat energy stored within the object. Ultimately, you don't have any temperature increase. This is a scenario that we can call thermal equilibrium, for a case where rate of heat received from the heater is equal to rate of heat loss to the atmosphere have become exactly equal. So this is the point. So when this is reached over here, as the question says that when then further temperatures are reset again. When the block reaches a constant temperature, the heater is switched off. So when this temperature curve became horizontal, it was switched off, and further readings are taken of this graph. The graph is shown over here. Now comes the question: suggest why the rate of rise of temperature of the block decreases to 0. I think I just explained that in terms of thermal equilibrium. Then comes the interesting question. After the heater has been switched off, the maximum rate of fall of temperature is 3.7 Kelvin per minute. After the heater has been switched off, the maximum rate of fall of temperature is 3.7 Kelvin per minute. Estimate the specific capacity of aluminum. So how do we do this? Let's try to understand the scenario a bit more vigorously. Have a look. This is the part that I want you to understand. Let's say there is a certain temperature at which the heater, the temperature is not rising anymore. As long as we keep the heater turned on at this steady temperature, the heat rate loss is equal to heat gain rate. The moment we switch off the heater, hear me out carefully. The moment we switch off the heater, it's going to keep losing heat to the atmosphere because it's still hot. But right at the instant the heater is switched off, no more heat is actually being supplied to the system. It means this would give us the absolute rate of heat loss at that instant, which means at the instant the heater is switched off, the rate of heat received just a bit earlier is exactly equal to the heat lost exactly at this instant. So if we can find out the gradient of this curve right at this highest point, or I mean most steepest location, this would give us, this gradient would give us the rate of temperature drop when heat loss rate is equals to 54 watt. Now see if you can make sense of this thing. The gradient of this tangent at the steepest point gives us this rate of temperature drop. I'm using rate of temperature drop because we have theta over here, t over here. So the gradient is going to give you theta over t, which is rate of heat loss. So this temperature over here is going to give us the rate of temperature drop when heat loss rate is equal to 54 watt. Does it make sense?
Yes, sir.
So for this, it is হ্যাঁ আবার বোঝাচ্ছি যখন টেম্পারেচার স্টেডি, let's say theta steady means what? Power in equals to power out. যখন আমরা সুইচটা অফ করে দিলাম তখন আর পাওয়ার ইন নাই, which means at this point we still have power out, and at the instant when the switch is closed off, you have to understand that at the steepest point of the curve is basically the starting point of this downward decreasing graph. at this exact point, the rate of heat loss should be exactly equal to the rate of heat in, which we provided from the heater, which we know for the value. 54 watt was the maximum rate of heat supplied. So at the instant when the power was switched off, the rate of heat loss should also be 54 watt. এই পার্টটুকু বোঝা গেছে কিনা? So এইটুকু বোঝা গেলে বাকিটুকু খুব ইজিলি সলভ করা যাবে। কেন সলভ করা যায় আমি তোমাকে দেখাচ্ছি। Because the question has already given us an information in terms of হয়ে গেল এই যে এখানে। After the heater has been switched off, the maximum rate of fall of temperature is 3.7 Kelvin per minute. So 3.7 Kelvin per minute. So you do understand this is a sort of a variable that gives us rate of fall of temperature, that is sort of like delta theta over T, which is 3.7 Kelvin divided by 120 second. That's basically the physical significance of this thing. The question is asking us to estimate the specific capacity of aluminum. We can do this. How? Specific capacity calculator formula হচ্ছে কি? Q equals to M C delta theta. So to be able to use the information that we have available, let's divide both sides by T, and I'm going to do it in a specific way. So Q over T equals to MC delta theta over T. This Q over T is basically the rate of heat loss, which happens to be equal to the rate of heat gain right at the instant of switching of the heater. And delta theta by T is going to be 3.7 Kelvin divided by 120 seconds. So if we place all these numbers over here, this is 54. Block of ice, aluminum ice block has 0.960 kilogram of this thing. I think I'm correct. What is the mass of the block? 940 or 960?
950 grams.
960, sir.
আচ্ছা ঠিক আছে। So this is 960, 0.960 kg. Multiplied by C, which is our unknown that we want to calculate, and then the delta T over T, which is going to be 3.7 divided by 120. So if you place all these numbers over here, you can find out the value of C pretty easily. At the beginning of the thermal chapter, not at the series, in the beginning, somewhere halfway in the discussion lecture, I actually told you that there are multiple different ways we can circumvent the problem of heat loss from the surrounding. This is actually one of the effective ways. So we have seen multiple ways. One of the ways was that we can take multiple different readings and eventually do the subtraction to get rid of the unknown error. That works. This is also another way where, other than using the lagging, we use the rate of heat loss as our measurement technique by heating up the heater to the steady temperature that our heater could possibly bring it up. This process, in my opinion, is really, really, really good, because we are calculating within the process of calculation, or within the method of doing this experiment, the loss to the surrounding is actually not affecting our results, because we are measuring the experiment right at the point where the supplied rate and the given up rate, heat in and power out, they are both equal. So it's a pretty smart way to do an experiment for thermal experiment, where we can circumvent, or we can get rid of the possible error caused by atmosphere. That's pretty much it for this question. It's a pretty interesting one, to be honest, if you ask me. The reason I'm actually giving so much emphasis on these questions, because whenever we're going to start paper 5, and we should start it pretty soon. You guys did not collect your paper 5 booklets, did you?
No, sir.
আচ্ছা ঠিক আছে, আমি মাউন্টকে বলে দিব, তোমাদের সেকেন্ড বুকলেট কালেক্ট করার সময় তোমার সেকেন্ড বুকলেট এবং পেপার 5 বুকলেট একসাথে কালেক্ট করতে পারবা. He's going to have them ready. I'll inform office. We have what, 10 people in our group, right? Maximum 10 people.
Yes, sir. Something like that.
No big deal. A gravitational question showed up over here. I don't know how. Oh, there's a bit of a thermal question over here as well. I think the remaining of the questions are actually pretty simple. I don't see much too difficult stuffs over here. Yes, question number 41. I'd like to give this one as your homework because I want you to make a logical decision of whether this will be underestimate or an overestimate. We talked about these two stuffs in one of our earlier lectures. Then in which cases, what you're gonna do, I want to try and solve this problem and come up with your own answer. You can be wrong. You're allowed to be wrong, which is perfectly all right. Just let me know what you think. And if you're correct, well then good. If you're not correct, I'll help you understand this thing in a more detailed fashion. That's pretty much it for today's class, I believe, because I don't see much to problems which requires really attention, because most of the problems are pretty much repetitive from our earlier problems. But I highly recommend that you try these problems. If you can do all of them, which is perfectly all right, at least try to do 50% of those. Try every even number, or try every odd number, or start from the back, starting from the last page. You go backwards by half the number of pages, or half the number of questions, whatever you feel comfortable with, and that's okay. At least try to do half of the problems to get a good grasp for how to apply the formula. You're gonna have enough time later on. I mean, you actually, nobody has enough time, and you can make time if you want to solve the worksheets, if you want. But it's important that you do the worksheets along with the class as well. So please go get busy, and if you have problems, let me know. Thank you very much. Assalamu alaikum.
Assalamualaikum, sir.